is not diagonal. Like your homework show you that M is not diagonal, right? But your homework 3, your Dembit matrix is diagonal. Your sleeveless matrix is diagonal. That means they are not uncoupled equations. They are coupled equations. So why one other advantage of monocoordinate is that I can write equations, scalar equations, like this. So the those equations here, the Q, if you look at them carefully here, I have a Q, J, double dot plus alpha plus beta for omega J, then Q, J dot. This is square, this is square here, plus omega J square Qj equal to Qj cube. All right. You have to be, the second equation is, I think, is something wrong here. It's supposed to be omega z, then alpha, there's no I there, and beta, omega z square, and qz dot plus omega z square qz. Right. And this is all scalar. This is scalar, this is scalar, this scalar, scalar, scalar. So the matrix equations, the whole matrix equation become n scalar differential equations. So this is scalar. Qj and j, and this j can be from 1 to n degree of freedom. So that is the advantage of monocoordinate. In other words, I transform a matrix equation motion to become the n number of independent scalar differential equations. This is all independent. See, J, this is scalar, this is scalar, 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 scalar. To solve a matrix equation is much difficult than to solve a scalar differential equations, right? This is all scalar. This is all scalar equations. So the monocoordinate, if they are proportional damping, will transform a matrix equations, a matrix equation of motion to become n scalar differential and differential equation of motions. All right. It is easier to solve this equation rather than matrix equations. In control, in some cases, we also like to transform to the monocoordinate so that we can design our controller for each decoupled equations. And this is our decoupled. We call decoupled equations. or uncoupled equation. Yeah, as they show here, called uncoupled equations. And there's another definition you got to be careful. The ith column of phi, the ket phi, is we call the mode shape associated with the ith natural frequencies. And if you plot it, this is shape. The shape, for example, the 101, if you look at 101, the 101 is the building, the beam like that. All right, this is, assume this is 101. And the first shape will be like that. That's my first shape. This is my 101. And this is the shape. This is shape. All right. And the second shape of the 101 most likely will become like this. Like that. That's my 101 second shape. There's a one point will cross the vertical axis. So that's the shape. So you can look at the shape, you can look at frequencies, and you know that your solution is correct or not. Okay, that's the way to do it. And so the model coordinates are commonly used in controller design. So that's why I use this, and you will see that maybe sometime next month, then we are going to use model coordinates to design controller. All right. Let us look at this 2D film example, simple example like that. All right, those are the two degree freedom system. Now the M is 1001 and zeta is 0.02, minus 0.01, 0.01, and so on. K is 2 minus 1, 2. And this W1 and W2 are absolute displacement. All right, so just answer your questions. If you write, you can see that the K, the mass matrix is diagonal for absolute displacement. This is some kind of property like that. For zeta and K, they are symmetric matrix. They are not diagonal matrix. And your homework, you can write in terms of diagonal matrix because your WD is the relative displacement. So you can write in terms of relative displacement, or you can write in terms of absolute displacement. And this case is absolute displacement, and K is the same thing. And we have two input, that's U1 and U2 input. We have three screen, we have three dashboard, Z1, 2, and 3, and we have two mass. Transformation, assume we have this phi, the transformation matrix. That's my transformation matrix. I can transform this, the M, I can transform them to become, well, this transformation, you know why I can use phi transpose here. It's supposed to be phi inverse, but I use phi transpose here. But it's just some explanation I need to give to you. The phi here, the transformation matrix, if you look at carefully, the system here, I have M W double dot plus there W dot plus KW equal to BU. Now, if I have a transformation like this, I say W equal to the cap phi, say Z. That's my new coordinate. And if I do this, then I can write in terms of M phi Z double dot plus Z phi Z dot plus K the phi Z equal to BU, and then if we have multiple the whole matrix by inverse M phi Z double dot plus inverse Z phi V plus dot plus inverse K phi Z equal to B U. Okay, that's my transformation matrix. So this is my new mass matrix. This is my new, this is my new Z matrix, and this is my new K matrix, the script K. So that's my M, script M, and my script K. All right. Now, for transformation matrix, we have to use this K-phi inverse. But in some cases, phi inverse equal to phi transpose. There's some transformation matrix that you can use that phi inverse equal phi transpose, because they are the same thing. And this matrix here, this K-phi here, is exact the same the property like that. This phi, only in some phi you can do that. Not necessarily all the phi you can do that. And this you can do that. So because we have this property, we can write this become the phi transpose M phi and the phi transpose Z phi and phi transpose K phi. All right. Now, if you do that, then you can find out that my new script M equal to 1, 0, 0, 1. That's become identity matrix. My script K is called phi transpose K phi equal to 1, 0, 0, 3. Be careful.